So policy gradient methods. Policy gradient methods fall under this particular branch of the model-free methods. We talked about PPO, A3C, and policy gradient. I don't remember A2C being covered in this deck, but I did see it somewhere in my Quizbot that I was trading with. So my Quizbot was basically a ChatGPT conversation that I used to prepare myself for the exam. But yeah. So basically the entire discussion on policy gradient begins with the idea that so far we've been learning action values, but we're going to try to learn a policy now without a Q table. And to do that, we're going to, instead of having a policy function that takes in a state in action, we're now going to have a policy function that takes in a particular theta. Did I skip something? Nah. So this theta will basically be a set of policy parameters, and they will be used to generate an action instead of remembering the action state entry, basically. So whereas a Q table would have a particular entry in a table for every state action pair, this policy gradient approach will have some kind of magical formula that'll take in some input parameters and then compute the best action to take at a certain state. We have this performance function J that takes in theta, and J is basically going to be a measure of how good these parameters are for the policy. So if we have a good set of parameters, then our policy is great. If we have a bad set of parameters, our policy is terrible. It's not going to help our agent maximize its reward signal. So since we want to have a high performance value, we want to maximize this performance function by taking gradient ascent steps. I think we had a question about this on the exam. I must have gotten it right. Maximization is solved by doing differentiation. That's pretty cool. Gradient ascent, that's what we use to maximize. This is a typo. We were talking about maximizing still. So again, gradient is used to maximize. How do you compute the gradient? Go to math class. How to parameterize. I think for this one, let's just talk about these two examples. So if you have a discrete action space, a softmax over the action preferences is a great way to go. But if you have a continuous action space, then you want to go with something more like a Gaussian distribution. It doesn't have to be Gaussian as long as it handles continuous spaces. So this is an example. This is the equation for computing softmax probabilities based on a preference function. This preference function should be defined somewhere here. So given a certain theta, you want to transpose that and multiply that by the feature vector for that state action pair. So that indicates your preference for that state. And up here, you're basically taking that preference and then exponentiating it to the base e. I'm not sure if I said that correctly. And then you're dividing it by e to the preference of all the actions possible from that state. So that is a way to indicate the preference for an action amongst over the preference for all the actions available from that state. So it's again creating a probability distribution that sums to 1 for that action. So there's an example where you can do some calculations to come up with your own. Is this similar? No, it's the exact same thing. I'll show you. It's just the answer down here. Okay. Gaussian, so this is the PDF function for the Gaussian distribution. Given a certain mean and standard deviation, you can compute the PDF. Parametric. So now you're just applying that PDF function to your parametric policy definition. And basically your mean and your standard deviation are the two components of your policy parameters. So right here, your parameter vector is expressed as a theta mu and theta sigma. And right here, we provide a bit more on that. Mean is approximated as a linear function. I do not remember why these equations are the way they are. I understood them for like 5 minutes, and then ChatGPT explained it, and I forgot again. So yeah, every time you get a little bit further into the mathematical foundation and theory, it's easy to get lost if you don't have a strong, really strong mathematical intuition of statistics and calculus. So definitely take a calculus course or a statistics course before you take this one. Don't be like me trying to drill down and understand the foundations from the top down. I should take my own advice and take a course after this in statistics. So, example of doing calculations using the Gaussian distribution, parameterize, what is this? How to define performance function J. For the episodic case, you can choose any state. But for the continuing case, actually not any state, it could be any initial state, I suppose, yeah. But for the continuing case, you want to think about averaging the rewards per time step. What else? Is this policy? No, this is policy gradient theorem, yeah. So there's a mathematical proof for this in the Bartusen book. If you love math, definitely read it. I took a stab at reading it, and it was actually quite elegant. There's a second part to the theorem that I didn't fully grasp, but it's definitely really interesting. The idea is that this is the way to express the gradient of the performance function in terms of the Q function in the policy, so that's pretty handy. This can be leveraged to implement our reinforcement learning algorithm. So the first example of that is the MC policy gradient approach reinforce. Pretty ironic how it's called reinforce. But basically you have this equation, and then you can use the, what is this? You can use the return computed for an episode as part of the target value. What is it? Yeah, probably, yeah. And then you use the gradient of the performance function to adapt the policy parameters. So update is proportional to return, as well as inversely proportional to the likelihood that the action will be taken. It's pretty obvious, but it's also proportional to the gradient, alpha as well, your learning rate. And then all that derivation you saw up here is put together in the algorithm right here on that one line. That's the update assignment for the parameter policy theta. And yeah, you might notice that part highlighted in red is actually an equivalent representation of the eligibility vector. So gradient divided by likelihood of choosing the action can be expressed as gradient of ln of pi of at given the st of theta. Yeah, policy approximation is pretty good. Instead of estimating individual Q values, we propagate our knowledge across the entire QS state space. Softmax. Yeah, you can inject prior knowledge. Oh yeah, so this switched corridor is a pretty good example of how things can become a bit more challenging especially when you want to build a optimal policy for using policy gradient. So in this particular example, you have states. All of them are deterministic except for S2, which has its action and transits reversed. So if you take left, you'll end up going right. If you take right, you'll end up going left. So the different epsilon greedy approaches don't end up getting really good performance evaluations, but if you try to build an optimal stochastic policy with reinforce, you kind of get there, right? But what? Wait, isn't there supposed to be another improvement upon it? Where is that? Is it the baseline? Yeah, they show you that with baseline it improves. With baseline you get that green curve up there. I don't remember why, but I do understand that baseline is basically modifying the values being added up right here, this portion right here. So instead of having just QSA, you have QSA minus BS, and they have some kind of proof regarding why that doesn't modify the actual function and why it all sums up to 0. Again, some part of the math that I did not dig further into, but definitely worth looking into if you're more of a math person. What is this? This updated. Yeah, this is with baseline. Yeah, this is how you would go about modifying the update equation if you want to go with a more TD type approach. So take out the GT and instead have a bootstrap estimate, R plus value of subsequent state multiplied by a discount factor gamma. Yeah, then we go into actor critics. So actor critics are a generalized umbrella term for reinforcement learning approaches that do both the prediction and the control problem. Policy gradient only does control. I don't know if I said that right. I might have messed that up, but policy gradients modify only a policy. Actor credit does both policy and value modifications. So here we have a set of weights to modify the values of states. So here we have a value function, and here we have our policy that's represented by an input theta. Again, they don't tell me what if it's prediction or control, because we had a question on the exam. I absolutely botched that one. Okay. And then advantage function is basically a function that computes how good a particular action is over the average action taken from that state. Sorry, yeah, for the state. Yeah, so that's all the policy gradient. Reinforce is pretty much the highlight of this chapter. And I don't think I talked about this example too much, but that's okay. Cool. Yeah, see you in the next one.